Thank you everyone for joining in our session, the second part of the BC Extreme events at the CMOS 2020 meeting. Here we are going to start with Tamar Richards-Thomas, and you can put your questions into the chat, and we'll try to choose them after. She's on the climatological context of the mid-November 2021 storms in BC. Go for it.
All right. So hi, everyone. My name is Tamar Richards-Thomas, and I am a research skills development trainee at the University of Northern British Columbia. I work primarily with Professor Stefan Derry and Ronald and Julie, who are listed contributors on this study. So today I will be sharing with you the climatological context of the mid-November 2021 floods in British Columbia. But before I do so, I'd just like to take the time to say thanks and acknowledge everyone who has contributed to this study. The province of British Columbia has experienced several large-scale destructive flood events over the past 21 years and even beyond that. But for most of us, the one that stands out is the mid-November 2021 floods in British Columbia that affected Abbotsford, Summer, and the Prairies. The image in the background of this slide shows sections of Highway 1 and surrounding homes that were flooded on November 16, 2021. And that provides a visualization of the severity of the destruction of this disaster. The mid-November 2021 flood caused severe damage to infrastructures and homes, and unfortunately, injuries and fatalities, thereby highlighting the need for understanding the climatological context of this disaster. The objectives of this study are to identify the factors that characterize floods in the province over the last 21 years, and that's inclusive of the mid-November 2021 floods, and also to identify a range of observed climatological factors that influenced and are related to the impact of the recent flood events. So over 30 flood events occurred over the last 21 years, as documented by the CDD, BC Ministry of Environment and Climate Change Strategy, and several news sources were used to conduct this study. Observed daily climatological data sets for the month of November 2021, particularly obtained from 3 sources, ECCC, 6 stations. We obtained total precipitation, mean air temperatures, and from the BCSS, we obtained, in addition to precipitation and air temperature, we obtained snow water equivalent and snow depth. From the Water Survey of Canada, we obtained mean discharge rate for about 11 stations. Bear in mind that the number of stations are dependent on the data sets that are available. So let's jump right into the results. The figure here shows a map of the locations and a polar plot of the occurrences and the longitude of the flood events that occurred over the last 21 years. So that is between the year 2000 and 2021. The legend shows us the flood types: heavy rainfall, ice jam, snowmelt, and rain on snow, and a mixture of snowmelt and ice jam. In figure A, we can see that the northern region, it receives a mixture of flood types, whereas the southeast is somewhat dominated by snowmelt. And along the western coast, we tend to have a lot of rainfall events. And so the mid-November 2021 floods fit into that. In the polar plot, we can see that there is a bimodal relationship, in the sense that it's dominated by a spring to early summer season and a fall to early winter season. In the fall to early winter season, we tend to see a lot of rainfall events and infrequent snowmelt, with ice jam occurring in the late fall to early winter. The mid-November 2021 floods also fits into this category as an extreme fall event. And of course, it was dominated by rainfall. An extension of that shows us a plot of the months against the years. And this is particularly for the flood events that were identified over the last 21 years. And we can see there are different types. And so there are two main takeaway messages from this. We can see that for the ice jam related events, they tend to occur in earlier periods of the last 21 years. But more recent times are associated with rainfall events, and the mid-November 2021 floods also falls into that. The gray shaded areas also tend to distinguish between these two seasons. So we can see a clear, spring to early summer season and a fall to early winter season. The figure on this slide shows us the graduated maps of the cost, the number of evacuations, injuries, and fatalities of these flood events that occurred over the last 21 years. In figure A, the cost is mainly associated with infrastructure and it varies over the province. But the number of evacuation, injuries, and fatalities, they tend to affect the more populated region, which is southern British Columbia. The mid-November 2021 floods was actually classified as BC costliest natural disaster with a cost of up to 9 billion Canadian dollars, significantly exceeding the total cost for all other events that occurred in the province over the last 21 years, which was about $0.2 billion. The number of evacuation, injuries, and fatalities are among the highest for the mid-November 2021 floods, with the evacuations up to 20,000, injuries up to 40, and fatalities up to 5. But we're grateful that the fatality rates are relatively low given the destruction of this event. The mid-November 2021 floods were triggered by atmospheric rivers, and they contained a significant amount of precipitation. Now, there are two ARs that were identified during the mid-November 2021 flood. The first was seen on November 11 to 12, and an example is shown in the imagery on the left in figure A. And the second was seen and found to develop between November 13th and 16th, as shown in figure B on the right. Figures A and B on this slide show the total precipitation as rainfall and the mean air temperature respectively. And this is plotted for the month of November 2021, so it's inclusive of the period over which the mid-November floods occurred. This data comes to us from the ECCC stations that were mentioned earlier in the methods. And so what we can see is that for the total precipitation on days before the flood events occurred are suspected to create favorable conditions for flooding. So this may include an increase in soil moisture. But on November 14th, we can see a very sharp peak in the total precipitation. And that is for all stations except for station OA. And this is as they experienced a significant amount of rainfall. In addition to that, the peak total precipitation recorded, the highest, was for station Agassiz CDA, and that is at 158 millimeters. So up to an order of magnitude greater than the total precipitation recorded on days before the event occurred. The mean air temperature peaks on November 12th, and that may be as a result of the first AR as it makes landfall with substantially warmer temperatures. But it also peaked on the 14th to 15th, which may be associated with the second AR. Now, the peak mean temperature on the 14th also correspond to that sharp peak in total precipitation as rainfall. The figures on this slide represent the climatological data sets for BC Snow Water Survey and the Water Survey of Canada data sets. In figure A, there is a steady increase in precipitation on days before the flood events occurred. And that contributes to snow water equivalent and the melting of snow in the mountains, which was significantly amplified by the events as they made landfall, such that the precipitation on around November 13th surged. And as a result of that, the snow water equivalent increase, and in some cases to some maximum value, which was first seen from the start of the month of November. In figure B, we can see that the peak year temperature occurred on the same days as those identified for the ECCC stations. And that is on November 12 and November 14 to 15th. But the temperatures are lower than those stations, and that may be as a result of these stations being at a higher elevation. Now, the peak year temperature on November 15 corresponds to the peak in mean discharge rate as a result of the continued surge in precipitation and also the intense rainfall that comes to us from the ARs as it exceeds 25 millimeters per hour. So to summarize the findings from this study, rainfall-related flood events, they are more common in recent years, and that can be seen along the coast of British Columbia. And the mid-November 2021 floods, it fit into this category as an extreme fall event. The mid-November 2021 flood events are BC's costliest natural disaster, and the highest number of injuries and fatalities were reported for this event in comparison to all other events over the last 21 years. Moisture and precipitation caused by ARs, they contribute to increased saturation and further create favorable conditions for flooding, whereas peak precipitation, it corresponds to a rapid rise in temperature over a short period, as you could see those sharp peak, and thereby contributing to higher mean discharge rate that are supplemented by snowmelt in the mountains. Further work, I will be using ERA 5 land data to explore the atmospheric moisture fluxes over the duration of these events. This is the end of my presentation. Thank you all for listening, and if you have any questions, let me know.
That's terrific, Tamara. Really nice talk, and thanks for keeping to your time so much. I haven't seen any questions come in. I was wondering if there were any people that had a specific question. If not, I do. I had a question. Did you also look, well, one is question is the seasonality of these changes. Have you seen a detectable change in the seasonality of the weather extremes?
In terms of the focus, that wasn't one of the areas I extended the study into, but it would be great to have a look at that for sure.
Great. And we still have time for more questions if people would like to type it in or raise your hand. I had another question is, have you looked at the impacts of freezing rain compounding some of the events that you have?
No, I also haven't looked at that, but it would be a great insightful piece to look at as well. So I'll just take notes of that as well.
Oh, I didn't need to put you on the spot.
It's okay.
Really great. One comment is they especially liked your polar plot of flood climatology. I very much agree on that. That's really great, and they're wonderful plots. And so thank you very much. So I guess we're just about on time to move to the next speaker, which would be Rupin Mo. And Rupin works with me, and he's going to give us another talk on this very important storm. There, you can go ahead, Rupin.
Okay. Yeah, this talk is about this weather conditions for this extreme flooding event. I would like to thank all my co-authors for their contribution to this study. So my talk will go with a little bit overview of the storm, and then I'll try to answer two questions. What were the major cause of this extreme storm, and how well was the storm predicted by a numerical model? Yeah, here I just show an animation of the satellite detected total precipitation water. You can see that within 5 days, there's 2 atmospheres were moving toward BC South Coast, and then the second one on the 13, 14, 15 actually penetrate quite inland. This slide actually showed the true water vapor transport. So you can see that this is the first event, and then the second is much powerful and coming in and stay longer in this area. You can see this anticyclonic flow in this southern BC area. So here you can see, just highlight these two driving force, quite cyclone, anticyclone couplet in this area, and then drive the moisture from subtropical area from Hawaii, and then we call it Pineapple Express usually for this kind of storm. And this is the summit of the model analysis. Here we say the anticyclonic flow can help channeling the moist air into the Fraser Valley for this case, and could also give rise to symmetric instability and slantwise convection for this storm. Dennis definitely just remind me of this mechanism, so I put it here. You can see the impact of the storm here, just 2 days precipitation in the Metro Vancouver area. You can see this orographic flow, orographic enhancement have much more over the mountain, and then near the mountain you have here, I think here's the Simon Fraser University area, get up to 200 millimeters, and even into further inland into Fraser Valley, you also see very significant precipitation. That's because of the orientation of this atmosphere. If we have cyclone-induced force, usually we can get a cyclonic flow toward North Shore Mountain. We get more precipitation over there. For this case, we have more channeling into the valley. That could be a factor for the extreme event, extreme flooding for this event. We try to understand what is the anomaly behind this. So this is the 5-day mean geopotential high of 200 millibar, and then 500 millibar over there. You can see a well-defined shortwave quite across Pacific basin there. It looks like it started from East Asia area and then go with this. So you can see here should be, let me see, here should be Vancouver. You can see this cyclone and anticyclone pattern over there. So this help to stay get this really stabilized ridge of high pressure just south of us. And then you can see from moisture transport, here is integrated water vapor anomaly with respect to the 30 years anomaly. You can see this plume of moisture coming up from Hawaii area. And then over here, I also plot the sea surface temperature anomaly. You can see this La Nina signal in the tropics area, and then subtropical and mid-latitude, we have this warm sea surface temperature in the Central Pacific that could also contribute to the atmosphere because the evaporation is much higher than normal in this area. This is the 5 days, I mean, from 11 to 15 November at the monthly mean, you also see that almost the same signal. It's a weaker signal, but the short wave pattern is still clearly seen on 200 millibar and 500 millibar as well. And then you can see the sea surface temperature normally in the Central Pacific area. So this is another issue we call Julian Madden-Julian oscillation. It's quite, the condition is like in this phase, they have phase 4 stay much longer during this period, in this month. And it's also the second year of La Nina. So try to combine these two conditions. So here's the diagram for like a MJO circulation. Usually this, when it go to phase 4, the upward motion move to this Southeast Asia area, and then trigger the convection. And then this is also the La Nina condition. We have this water circulation move the convection over the maritime area. So it's the same location of this phase 4 of MJO. That could be the one reason, because for this stationary MJO signal over here for much longer. So that, well, let me see here. So the combination of these two mechanisms could be the reason that force this circulation anomaly. This kind of a Rossby wave propagate along the Pacific basin here. So we get this very strong anticyclone flow over there. Here, I try to examine how well this AR system was predicted by our Canadian global model, the global deterministic prediction system. You can see on the left hand here, you can see this is an analysis of the model and also analysis of the ERA5. Almost it's very good. Compare these two analyses, and then you can see 24-hour forecast is very good. Get right on, and the penetration almost the same. And then up to 48 hours, still very good. 72, day 3, day 4, even day 4, the location maybe slightly moved to the north, but the system is still well predicted by the model. Then up to day 5, slightly worse, and then day 6, the timing may not be that good, but at least the signal, atmospheric signal is there. Here's the precipitation, 24-hour precipitation forecast by the global model. Global model here. You can see that up to 78, there's some flip-flop of the amount, but the signal of heavy precipitation in southern BC, coastal BC, is there, up like up to like day 4, day 5 forecast. And we also have this very high resolution model. We have the 2.5 kilometer resolution, this national model across the nation. The forecast, I just pick up one station to highlight this Hope, observe 174 millimeters, and then this high-res model, 2.5 kilometer resolution, pick up 147, slightly under forecast amount. And then we have this 1 kilometer resolution model just for the Western Canada. It get the amount higher than the observation. So overall, I think they pick up the range of this event for this 24-hour period. And then we even have an experimental model with even higher resolution, is 250 meter. We run this model after the fact, just try to see even to see how this model can handle this topography feature for this storm. Actually, it's quite good. I didn't have time to go into detail, but I just show one. This is hourly precipitation and compare with the observation there. It's actually quite. It gets more detail of the structure and the distribution of the orographic flow, orographic precipitation. So I just try to summarize the result. In November 2021, we have 6 major atmosphere. I think Bobby counts as 7. I may merge one of them together. So it's much well over climatological norm for this month. Then the AR induced convergent warm and moist flow led to this extremely heavy precipitation of the complex terrain in southern BC. And we identified a North Pacific shortwave chain was responsible for the stable cyclone anticyclone couplet driving this driving multiple ARs onto southern BC in November. Then the shortwave chain had its origin in the tropical area over Southeast Asia, forced by the combined effect of MJO phase 4 and the La Nina conditions. The major AR was correctly forecast by the operational weather models up to at least 4 days in advance. And but I think the hydrometeorological impacts of AR could be underestimated because something may not be in the model, and the model also have some uncertainty in this this forecast. That's my talk.
Terrific, Rupin. Thank you very much. I don't see any questions. You guys, you can type your questions into the chat. That would help. Or of course, you can always ask him later. So Rupin, I was wondering, I can ask a question. What do you think about being able to take in long range forecasts to help assess these and even go further than 2 days to 4 days out to a few weeks? What do you think we need to do to be able to provide longer range forecasts with some accuracy?
Yeah, I think this is a good question. I think right now for deterministic forecast, we can get maybe for atmosphere, we could get some reliable forecast up to 7 days. But beyond that, we need ensemble model, and we also need to do this interseasonal forecast, especially pick up the MJO signal and maybe seasonal model forecast to pick up the El Nino or La Nina effect. That could help us better handle this kind of extreme situation. I think the other issue that could be related to the polar ice loss of there that could like a recent study that showed that also triggers some circulation anomaly similar to this one. So I'm not sure that could help.
Well, that's a good answer. And we have a couple minutes before Matt will present. We have a good question here from Vanessa. She's wondering if the persistent high pressure system over Southwest US has led to a multi-year mega drought is influencing storm trajectories in BC. She's read that the historical mega droughts in the US have been related to the above average precip. You see, I know you've thought about this one.
That could be. I have another talk later. It's about the June heat wave. That's we also have a normally high pressure system over there related to this. So for this, Professor Ken Moss mentioned that we have this jet stream move northward, and then we also have this subtropical high move northward as well. That could have this impact as a climate change signal in this area.
Yeah, that's a good answer. I'll try to grab one more question here. And Matt, if you wouldn't mind sharing your presentation, or Rupin can stop sharing. Rupin, here's one more question from Nathan. Climatologically, is there a link between ARs in this region and ENSO? Are there more ARs expected in La Nina conditions?
I think so. This a study actually showed that with La Nina, we have this how to call it, jet stream move further north that could bring more atmosphere toward our areas and even further north.
Yeah, well, great. We'll combine those questions and give everyone a chance to answer. If you have more questions, please enter them. Next speaker is Matt Seckles, and he's going to give us another great presentation. Go ahead, Matt. Matt, we can't hear you, of course. Can you start your video and your sound?
There we go. How about that, Mandy?
That's great. And when you
Okay.
see my poofy hair come back, it means you have 3 minutes. I
Okay.
haven't had to pull it out yet.
Okay, great. Okay, well, here we go. So thank you for having me here to talk about my wet weather shutdown guidelines project. This is a project I've been working on for a few years, but it's just changed relatively recently when I was able to connect with Ruping and Mindy and the ECCC crew. So, and that was Matthias Jakob that made that connection for us. So that I really appreciate that. So helping me along with the project are Ben Kerr and Sina Shabani from Foundry Spatial. So the image I have here on the left really encapsulates what I'm after here. Here we have an active setting here sometime after the storm, obviously, because the sun is nice and out. But you can see the pickup in the bottom of the frame. And just before this landslide happened, apparently the forest workers were in the pickup. They were having their lunch, probably hiding from the rain on this switchback. And for some reason, they decided to move the crummy just along the road a little bit. And then the landslide happened. So it's very fortunate. And otherwise the investigation would have been much grimmer. But this is really that encapsulates what I'm after here. So how do we predict what's happening to these? And so our problem is that current shutdown guidelines for earthworks and timber harvesting are related to on-site rain gauges. So once a threshold is set for, or thresholds get set for a particular work site, and once those thresholds are exceeded, then we shut down. But that's only after we get to the site and look at the on-site rain gauge. So it's a very reactive system. There's no proactive component there. We also don't get records on non-work days, which makes it more complicated to piece together what's happened at that site from those rainfall records. And there's also a bit of a negative incentive to report exceedances. So you've already made it all the way out to the site and it's just slightly above the threshold. You know, there's going to be, and I'm not suggesting that this necessarily happens, but I can see that there is this incentive for a little bit of that water to get spilled out, that rainwater to get spilled out. Otherwise, it's paying your workers and bumping down the forest road back to camp or back to town. So without doing any work for the day. So we also have some exposure to get to the on-site gauges, but as we look at risk along roads, it's typically relatively low. So we're seeking a proactive system, something where we can plan the work, particularly when you're doing road building, when you're working with difficult sections or you're about to move into a difficult section. If you had advanced warning that a storm was going to be arriving, you could maybe hold back from opening up that difficult portion of terrain. Or you know, if you'd already opened it up, you could make sure that you put it away well so that it would drain acceptably while you were waiting out the storm. So this is all about limiting exposure to workers from landslides. So in previous work, we've evaluated various forecasts against observed data across the BC coast. And what we found was that, not surprisingly, we had relatively poor results for hourly levels, better for daily, but we suffered from a lack of storm data. And it was also relatively expensive to gather this data in the past anyways. But now we have integration with the ARC Superstorm project with Midian Rooping, and this allows me to stop focusing on the atmospheric end of things and move towards the terrain and geo end of things where I have more expertise. So I can focus on the impacts. So in terms of the analysis for the geo side, I'm using volunteer erosion event records since that I've been collecting since 2017. This is something that was collected in the past, and then we had a couple decades there where it kind of went on hiatus, but I'm trying to reinstate it. So this is non-systematic. These are people who are out on the forest roads. Maybe they're doing patrols after significant storms, and then they're finding landslides and reporting them to me. Or maybe they're just doing their general work and they discover older landslides. So the event timing is one of the sources of errors I have. Sometimes we get events that are tied nicely to an event, to a hydroclimatic event. Other times it's a discovery sometime later, and it's loosely associated with a particular storm. So I had collected data on 75 events, but we only had 42 with good data. And that's related to event timing, the spatial data of the occurrence of that landslide or feature erosion event, and confidence in that report. There are some more available, but I'm gonna have to do some more digging to get there. So, right. In terms of the analysis on the atmospheric side, so we use the Canadian Surface Prediction Archive. So they're all forecasts, and this is using the high resolution deterministic prediction system. So its access back to 2017 covers almost all of my modern period of erosion event recording. And it does include the significant storm that affected Northwest BC. It was an atmospheric river, I believe, as well, in late October of 2017. So I have more mining to do of that data that I can put into this model. So we do have some issues with this model continuity because things are changing all the time and improving, but that does lead to some issues with continuity. Apparently the data was very easy to work with. The Foundry folks really appreciated that, and we used the 2.5 kilometer grid. So there was some options to use some other grids, but unfortunately they excluded Northwest BC, where most of these events are. Okay, continue to describe what we did here in terms of the atmospheric side. So we collected spatially explicit forecast data for time periods prior to the events. So we looked at a range of times. So from 3, 6, 9, 3, 6, 12, 24, 48, and 72 hours, as well as 1, 4 weeks, 3, 6, and 12 months. So all the way from the very shortest term out to quite long term. And so we only looked at precipitation amount. I recognize that the air temperature or the wind might drive some snow melt in particular, but we just focused on precipitation for this first go round. And so what we did was when we had an event, we looked at over these time periods, the maximum precipitation percentile in that period relative to the entire data set for that location. So so this is really important, and I think that it's a good approach because typically a lot of landslide investigations look at just the millimeters, say, of precipitation at the site, and that changes very drastically between the hypermaritime environments on the coast and the interior environments towards the east. And so the soils are different, the vegetation is conditioned differently. So I feel that looking at these percentiles relative to what that spatial location is accustomed to experiencing is more important. So we're looking at these forecast precipitations over those periods relative to the entire record. And unfortunately, we have like a little spatially relevant validation data available. And so that is always a challenge. So we ended up with And I've bolded shallow landslides here and deep-seated landslides because that's where my main focus is, but the others came along because they were also reports. So 19 shallow landslides, 6 rock failures, 2 snow avalanches, 6 deep-seated landslides, and 9 stream flow events, both nival and pluvial. And then when I'm looking at the hydroclimatic forcing, this is kind of my hypothesis of forcing. So for shallow landslides, this short period, very intense rain, as well as a 4-week period that Matthias Jakob found up in the North Coast back in, and he published in 2006. Rock failures, snow avalanches, both I think on the short period, deep-seated landslides on the longer side, and then stream flow events split between longer for nival and shorter for pluvial. And let's see, here we go. Here it is. So surprisingly, or not surprisingly, we see on the top, we have a pluvial response from stream flow. Yes, so the erosion events that are occurring are often bank failures or deposits of significant sediment. And then the nival is somewhat less, it's still responsive to the very shortest periods, less than 1 day prior to the event in that very short period. So the high intensity there is coming through on the snow avalanche or on the nival flows, as well as the snow avalanches. The snow avalanches here in the white. The rock failures really didn't seem to be that responsive. They tend to happen more when it's been raining a bit more, but kind of no pattern there in terms of temporally. So, but looking then at the deep-seated landslides, I was shocked to see this. You can see that it's a very high percentage. So it's of that entire period prior to those events, that's where the most intense rain was forecast for those over those periods. And I was very surprised that this was much higher than the fuchsia there for the shallow landslides. And so found that very surprising. And I did lose some sleep over that. So. So when I looked at the plot of shallow landslides, we see again, there's one oddball there down low, but in general, it's kind of the 80th to 90th, 80th to 100th percentile of those storms over those short periods that are driving those events to occur. And in the deep-seated failures, even higher. And so I was trying to tease out why this might be. And so I broke these up into the blue lines being deep-seated landslides that are that will end on in stream channels where the elevated stream flow might reduce that toe support through erosion and induce more flow. And the green being those landlocked sort of deep-seated landslides. But not really a heck of a lot of pattern there, and definitely a shift to the lowest periods. So and effectively what I've come to think, what my hypothesis currently is that deep-seated landslides are some things that that continue, and so that they're kind of continuously happening. And if you recall, these are submitted erosion event reports. So after we have a period of very heavy rain, I think people are more accustomed to go check out their local landslide. These deep-seated landslides, many of them are kind of in near towns in more populated areas. So so they get identified and reported on after some heavy rains. So I'm expecting that is why we see this pattern. So in the future, I mean, the erosion event reporting system is excellent, and it's nice to have people involved and reporting what they see out in the woods. But I'm also now interested more in automated landslide identification so that I can have a better idea of or a more unbiased collection of data there. So I'd like to continue to work towards developing shutdown procedures based on forecasts in the context of antecedent conditions. And those antecedent conditions here captured by those forecasts, but having some sort of calibrated, recalibrating those forecasts for what actually fell would be great. So they're spatially and hazard specific, and I think that's really important for these for shutdown procedures moving on towards the future. So we're looking for things to be safer for our workers and to have fewer landslides in the environment. And that's all I have for you today. Thank you.
Hey, Matt, that's terrific. And I'm so appreciative of you coming and joining joining the group and helping and focusing on landslides, which is, they're so important. I was looking for questions that people had. Sorry if I didn't see it, but I really liked your analysis and separation of deep-seated landslides and shallow landslides, and your description of that, the ones that are undercut by a river flow versus those that are not. Those are really terrific. I was wondering if you could comment more on that, and then also give us some more feedback on what antecedent values would be best for us to calculate to help you do your rating.
Right. Okay. I mean, I guess in terms of antecedent conditions, I'll address that first. Is that, I mean, it would be really nice to have some sort of calibrated estimate of what has fallen in a distributed sense, because the antecedent conditions are so important for landslides and for flood generation. But I mean, for flood generation and snow avalanche generation, that's often, you know, we have the River Forecast Center, we have Avalanche Canada that are dealing with those. So that's why I kind of focused on just the shallow and deep landslides. So, but also like, especially on the coast, when we have significant rain on snow events, knowing the snow water equivalent that's on the ground, they're available to melt into, to infiltrate into the soil would also be really nice to know. So I guess that's the wish list in general. And when I was talking about these deep-seated failures, yeah, so I mean, these are relatively close to town because they are low in the valley bottoms often. And I just have 5 instances here, and so a couple of them are, or 3 of them in particular, are next to rivers. So these are sort of deep-seated failing banks that are monitored relatively closely by people that live in the neighborhood or road users on roads that traverse above them. So so I had the idea, and I mean, this is all sort of me sort of trying to tease out why we have a difference between the response to those deep-seated failures and why those deep-seated failures had even more dramatic, more intense, more precipitation relative to their own site than the shallow landslide triggers did. So I believe it's because of the reporting, but more data, more work to come.
Oh, well, that's part of it. It's going to be many years to get everything right. But what strikes me is how much you care about the people's safety and doing your job and reaching out. And that's all what we're trying to do, is keep people safer, and we will together do better. Ashley has a question. She asked, could we also extrapolate this work to the underlying variables driving it to also refine the areas of high landslide risk?
Yeah, certainly. And really, I mean, that's kind of what I was getting at the end there. My conclusion is that I'd like to see that when we have oncoming storms, that we can then predict in particular areas, yes, okay, these areas are now going to be subject to deep-seated landslides. And historically, I think, or like, you know, from the literature, that's going to be when we have long-term elevated levels of precipitation or snow melt inputs, say. And then and on the other side, with the shallow landslides, when we have more intense precipitation coming over shorter periods, those are typically what drive those shallow landslides. So we can use that as the atmospheric side, and then we can meld that with our terrain stability mapping and the terrain stability work that we do in the forest industry and in the construction industries to try to reduce our landslide hazard for our workers, reduce our landslide risk to the workers. Yeah.
That's a good answer. Just to let everyone know, we've stolen some of our 10-minute time. So if people have to run out and get a drink or something, they can. We may ask Matt I have another question for you. And Trevor's talk will start at 13:50. So if you've got 6 minutes there.
Okay.
But Matt, so appreciate you here and your energy and enthusiasm. I just know you're going to save lives. Is there any, like, what are the things you plan to do in the future that would be like your long hanging fruit, something you really, really need from us?
Right. Well, I mean, I guess that's it. I'd like to see, like, I mean, being aware of these now, these high dense, the high resolution deterministic prediction models system, that's excellent, and that really changes the game for me and the way I can approach managing the land from a landslide point of view. But having that calibrated, knowing what actually fell relative, like knowing what those errors are, like Ruping was getting to a bit in his presentation, knowing what those errors are, what level of over prediction or under prediction we're dealing with in general would really help us to, would really help me to understand what's happening on the surface.
Well, that's terrific. We'll just get you with one more question because you're a tough guy. Vanessa has one, and then we will give people a little bit of a break and ask Matt, not Matt, ask Trevor to put up his presentation. Vanessa asks,
yeah, go ahead.
And you could read it too, but I'll just read out. Any plans to look at storm trajectories related to landslides in your study area? Outside of ARs, westerly flow, westerly approaching storms typically bring significant precip for this area of the province, which might be a shutdown indicator.
Right. Yeah. I haven't done that, and that's why I was happy to connect with your crew so that you could handle. We could get more of those atmospheric products from you, the prediction products. So that's definitely a possibility. Like, of course, that makes great sense. I just really enjoyed being able to use the prediction service and not have to wade too far down in the atmospheric side, and so that I could focus on the landside side. But yes, certainly, if there's something more that could be added to the high resolution deterministic prediction system or like another level, then that would make good sense.
That's
and
great.
I saw there was a question from Serena Renner, and it said, I've heard that logging roads themselves create landslide risk. Are you looking at what can be done in the process of road building or choosing not to build roads in high risk areas to increase safety? And certainly there's a lot of work that's gone into that by many people. And that's really why when we're working on, when we're building road in areas where there's elevated landslide risk, that you have a professional assessment on site that and they kind of walk the roads and make recommendations on the road design so that to minimize those hazards. But things still happen, and so being able to, and one of the things is that often if you can, a particular road can get built, and of course I don't know this, but it would seem that if you could build it in dry weather, you'd be able to build it and the road would stay together. But if you try to build it in wet weather, everything falls apart, and you end up with worker safety issues and environmental troubles.
Great answer. And sorry, Serena, I didn't have it full screen. I missed seeing your comment. Do you feel up for answering the last one? Nathan has a question. We still have 2 minutes.
Right. I mean, yes. I mean, I think that many people are working on automated detection of landslides. So we've got to incorporate those. As yet, I was just using. I haven't been involved in those deeply yet, so that's why I was using those erosion event reports. We're driven in part by the wildfire. It's summer 21. Yes, co-location of landslides and burn scars. Yes, very much so. I think that's definitely something that is happening, and so yes, more work to be done.
Did you see Nathan's question? Are there remotely sensed landslide products available?
Yeah, I think that there are, and I think that there have been for quite some time. The problem was that the level of error and the level of assurance you had that it was actually a landslide, not a recent cup block, not a stream channel avulsion, things like this. But I haven't checked in with them for a little while, but I would assume that, like everything, it's getting much better, and I now have increased and renewed interest in looking at that.
Great. Well, I think we'll wind it up here, and if we have more questions, we'll be sure to get you to answer them. You can answer them as we go on. And we have 1 more minute before Trevor gives his talk. If Trevor wouldn't mind sharing his now, and Matt stopped sharing, that would be great. Keep us on time.
Thanks very much.
Thanks, Trevor. Matt, you can stop sharing your screen, although we love seeing you. Right.
Bye-bye.
But we would like to see Trevor in right now. Trevor, you can start anytime.
Okay, great. Thanks. I'm Trevor Murdoch. I'm a climate scientist with the Canadian Centre for Climate Services. I'm going to be speaking about some work that all of which was done at the Pacific Climate Impacts Consortium, which I was until fairly recently. And Zane Sloan, I'll pass to in about the middle of the talk, and he'll be talking to, the theme of this year is Science Serving Society. So he's an engineer who will be speaking to how does this future projections that we produce serve real human beings who use it for decision making. So just I want to very quickly give the 30-second description of this kind of what goes into a risk assessment. If you haven't seen this before, this will be too quick, but just to make sure you've got the basics. We talking about this particular kind of risk assessment called PIEVC. You can quiz me on what that stands for, but and like many climate risk assessments, just break risks into consequence and likelihood. So how bad would it be if something happened, and how likely would it be to happen? And where the climate projections tend to come in is pushing the likelihood further to the right, to higher numbers. And so you actually will assign it's sort of a expert elicitation, semi-quantitative, semi-qualitative, but creating actual numbers with both of these values, and you multiply them together to get the risk. So if you have a very likely event, so in this case, the event that was looked at was so there's a bunch of different climate parameters that are looked at. These are the columns here in this screenshot I'm showing you from the risk assessment. And there's two where the highest risks showed up. One of them was an extreme rainfall event of 76 millimeters in 24 hours. As we heard earlier today, this is actually a fairly small, quite a bit smaller event than what just happened. But the way these risk assessments work, this is roughly order of magnitude 1 in 10 year kind of event by 2050s. And if we were to look at an even more extreme event, the consequence can't get any larger. So if you look real closely here, some of these actual numbers, I don't want to dwell on them too much, but the ones that are in red are 42. So that's a 6 times a 7. This was using a system that had 7 categories on both those axes. And so the consequence would just be, it's already maximized. These are events with a probability of 6 out of 7 on this scale that they were using, and a consequence of 7. And so the other event, the other item that led to a large consequence was storm-driven peak flow. And there was no direct projections that went into that. That was just expert opinion based on the projections we were looking at. This was really early days. It was actually, I think it was the very first risk assessment that PIEVC was involved in. And so at the time, we were just using 3 regional climate model projections from NARCAP, the sort of predecessor to Cortex, with a very simple sort of threshold scaling to observations. And so that was the basis for assigning this as a probability score of 6 in future, something that would have been 4 or 5 in the past. So that's how you get the change in risk. So all 14, so 14, you can't see them all here because I'm not showing all of the different infrastructure components that we're looked at, but all 14 of the high risk interactions were related to atmospheric rivers. And so this, I thought this quote was sort of pertinent from this report, that based on the risk assessment, the Coquihalla is generally resilient to climate change. There's some other risks associated with the temperature extremes and the sort of percentage of bitumen that you put in the pavement, but all the high risk stuff was related to atmospheric rivers or Pineapple Express. And so this led to a pile of work. Oh yeah, I forgot to take the animations off here, but we have, so PIEVC subsequent to this did a couple of reports on the state of knowledge of atmospheric rivers, future projections of atmospheric rivers, a best practices document the province put out of how can we, in new builds, build highways that are less vulnerable to these more frequent events. And all of that kind of culminated in the thing where I met Zane, who I'm going to hand over to in a moment. to this technical circular. So this was essentially the first requirement of any jurisdiction in North America, perhaps maybe some municipalities, to explicitly require future climate be taken into account in all new builds. So only in anything new that was being done subsequent to that time. So we've had that in place in BC for highways since 2015. And then finally, professional practice guidelines from engineers and geoscientists of BC came out just in 2020. So the main message here, look at the 10 years between the risk assessment and the professional practice guidelines. The message, it takes some time to get to professional practice guidelines. One other thing I wanted to mention, because it'll be of interest to this crowd, is that it also sort of indirectly, not directly, but played a part in making the case for an investment in precipitation downscaling techniques, which improved the statistical downscaling methods that are in place at PKIC. Okay, so if we knew all of this in 2010, how did this happen? That's kind of the the $24 million question. And basically, what this comes down to is, I like to think of earthquake risk in the 80s. We went through this, we first realized there was much more seismic risk than previously, and there are still high schools around here that are being torn down and built back up or retrofitted. It takes some time before you actually get to the place of looking at existing infrastructure. We have this sort of massive amount infrastructure deficit or adaptation deficit, all of this infrastructure that was built in a static climate conditions. Coquihalla is actually one of the newest highways in BC. So even if we knew this was going to happen, we wouldn't necessarily have been able to find money to go sort of replace infrastructure that's perfectly good. So we're on this sort of path we're getting right now. There is actually no explicit requirements to build back better upon replacement. I think this event is really pushing us to do that. Let's make sure we don't just replace like with like. And with that, so we're getting to the last stages. With that, I'll hand over to Zane.
All right, thanks, Trevor. And in the theme of building back better, there's another place where we have to build back better. This is like the little brother of the November disaster. This actually happened in the spring of 2021 and the spring of 2020. And these are landslides, like Matt was talking about earlier. So here's the legend of what happened here is in late 2019, in the late fall, it got lots of moisture on the ground, soaked the soil, the earth got soaked, it froze in place, and in the following spring, it melted quickly. The snow melted quickly and it rained on top of that. So basically, earth turned to mush, and we end up with these 10 landslide sites all up down the Caribou corridor between Williams Lake and Quesnel. Next slide. So we got this project. We got to replace these highways that have fallen apart, and we're in the middle of planning and designing. And the planning process certainly focused on the landslide challenge. That's the biggest vulnerability that we have. So the planning is doing that, but what do we do with design, and how do we design for resilience? So we looked at the past PIEVC protocols, those things that Trevor was involved in back in 2010 and whatnot, and see that we can see in this map, there's been 5 PIEVC protocol climate risk assessments done in a province in these different climatological regions around the province. So we thought, well, should we do another PIEVC protocol was the question. Is that going to give us the resilience? So we thought, well, let's take a closer look first at the results for the past PIEVC protocols, those past climate risk assessments. Next slide. So we discovered that in those past climate risk assessments, it concluded, after looking at about 100 different categories of infrastructure along the highways, these 14 categories consistently came back as a high risk item. So if you think about the flood in November and all the things that fell apart, everything falls inside this list. You got your embankment cuts, you got your hillsides, you got debris torrents that came down, structures that cross streams, there's your bridges, right? Anything in the river pretty much, culverts of various sizes, et cetera, et cetera. So these are the infrastructure things that are at risk. Next slide. Looking deeper into those protocol assessments, we can see that everything's about the water. These are 5 climate hazards that all are water connected: extreme rainfall, heavy sustained rainfall, peak flows in the rivers, and snow melt, of course. Okay, so we know that. Next slide. So now what? So we know if these are the infrastructure that's at risk and we know what's causing the damage. We saw that we know the theory, we got it figured out. In November, the flood disaster provided the proof that that's really what's at risk and what's causing the damage. Next slide. So what do? Well, enter stage left, the PIEVC high-level screening guide. It's the same philosophy as the PIEVC protocols that Trevor were involved in and around the province. But this is a streamlined approach. It's basically just a spreadsheet. Engineers love spreadsheets. So this came out just in February. It's brand new. And we thought, well, let's see if we can leverage this. I'll show you how, well, and I'll show you how it works right here. This basically fills the gap. This is the spreadsheet that is the PIEVC high-level screening guide. And the top row, there's your climate hazards. And we've got the 5 climate hazards in there, but you actually can count 8. The reason why we have 3 more is because we duplicated 3 of the hazards. For example, that first hazard is maximum 1-day precipitation. The next hazard is still maximum 1-day precipitation, but we consider, well, what happens if it's fire scorched earth or on mountain pine beetle infested area, or there's logging operations going on? We considered those ramifications. The column on the far left, those are your design elements. So those are those 14 infrastructure categories. But what we do is we hand this spreadsheet pre-populated with these hazards. We hand this spreadsheet with these categories to the designer. So give a design team who's maybe got a 3-kilometer piece of road they're designing. They'll actually insert the rows of their actual infrastructure they're designing now. And this fills a big gap in the process. Now we're actually doing the engineering. That was what was missing during the protocol assessments. They did some engineering, sure, but they couldn't really get fine-tuned on each culvert, each bridge, each hillside. Here we can. So during the design process, we drill down into the actual infrastructure. Next slide. So this is what it looks like in the end. We actually, the designer gave us back the spreadsheet with their actual infrastructure. We held a workshop and we went through all the consequence scores and talked about all the consequences. And you can see the second from last column on the right, all that text in there. That's all the discussion we had about the consequences that could happen in each of these cases, each of these hazards. And that those red listed items there, you can see that would cause the most discussion for sure. And the far right column, those are our recommendations for adaptation to climate change. And this is how we get resilience in our design. Once we understand what and where the risks are, well, then we can adapt the design. Next slide. So that one high risk item, just to show everybody what did we discover was actually at high risk in this particular design project. This is a roadway cross section. You can see our little 2-lane gravel road down at the bottom. The designer refers to this part of the design as the Grand Canyon. And we're cutting each one of these grids is 5 meters. That's 5, 10, 15, 20, 25, 30 meters deep we're here. And the risk we saw was from potential landslide, that the factor of safety being designed for this slope is 1.56. But the question is that 1.56 only good for 2022, current day, or will the factor of safety still be the same in the year 2100? Likely not. And that's what the engineers now have to go back and study to figure out whether or not they need to adjust the factor of safety, accept something different, or change the property we're acquiring. And with that, I'm done. Back to Trevor.
Okay, so just to summarize here in our last minute or two, quickly rush through some of sort of the evolving role of risk assessments. The Coquihalla risk assessment in 2010, that really the answer to how could an atmospheric river happen, even though we thought about this, more than a decade ago, is that that wasn't intended to try to prevent all damages from such events. It was it was trying to get the the buy-in to be able to start requiring new designs to be built to take future climate into account, like the one that Zane just walked us through. And so we're getting to, in terms of this, you are here, build back better. We're past the stage of designing future climate. We're actually not just doing risk assessments on existing infrastructures to highlight the vulnerabilities. We're actually designing new infrastructure for future climate. We're starting to get better at replacing failed infrastructure with new components that will actually last through a changing climate. And And the next bits are, oh, should we actually start, doing some explicit analysis where we find the sort of the absolute highest risk category, the low hanging fruit of highest risk, go back and actually do early replacement. That's kind of a cutting edge, but that's maybe where we're going. So for those of us involved in climate services, I think we can start to expect to have questions from users about that. So that's it.
Well, thank you. That was a great talk, Reverend Zane. And right, we don't have much time, any time for the next talk. So please, people, put your questions in there. I have questions myself, and I think what you've done is great. And for us, it's just what we need. We need much more information on consequences and variables that you need to help track those. So, to keep on schedule, Stefan, would you be able to share your screen? Stefan is a professor at UNBC, and he is going to give us our last talk. I believe he does actually have a half an hour, but he said it's 15 minutes, so you can go longer if you wish. There you go.
Thank you so much, Mindy. I did not realize it was 30 minutes for this last presentation in this session. Thank you so much. I'll probably last about 15 minutes, but thank you for the opportunity to present in this session. And I'll be presenting on behalf of a large team of co-authors, as you can see here on this title slide, particularly some colleagues at the Université du Québec à Montréal, Dr. Julie Thériault and her team, as well as a team of researchers and students at University of Northern British Columbia and Prince George. I am presenting from the Prince George campus of UNBC, which sits at the confluence of the Nechako and Fraser Rivers on the traditional unceded territory of the K'ch'tene. I'll be presenting on a field campaign that we held last fall called the Tatsa Ranges Atmospheric River Experiment, or TRARE. And our team was in the upper Nechako watershed, and the Nechako is the second largest tributary watershed to the Fraser River. And it is a regulated system. And so Rio Tinto manages the Nechako Reservoir. Tatsa Lake that you see on this title slide, there is a tunnel, actually a 16-kilometer tunnel from the west end of Tatsa Lake. And water is diverted towards the Kamado powerhouse. That is a 900 megawatt facility, and power is generated there, transmitted to Kitimat, where the Rio Tinto aluminum smelter is. And of course, we've heard a lot of talks today about atmospheric rivers and their importance in terms of floods and just water replenishment. So that was part of our motivation here. So indeed, we know that atmospheric rivers are very important in terms of water replenishment in British Columbia. Some previous work that we had done by PhD student Asim Sharma showed that on average in British Columbia, about 10% of the annual precipitation derives from atmospheric rivers. That can actually increase to about a third of the annual precipitation along the coastline of BC. But as well as we know now, like in mid-November 2021, they can bring adverse conditions and flooding. Some of the previous work, again, that Asim had led showed that we get, on average, about 35 annual landfalls of atmospheric rivers along the BC coast. That goes into southeastern Alaska. And the two busiest months are September and October. So each can get about 5, on average, landfalls. And despite this, there was no prior field campaign, to our knowledge, that was dedicated to monitoring atmospheric rivers in Western Canada. So again, that's why we initiated TRARE. And given that September and October are the busiest months, we held our field campaign in September and October in the upper Nechako watershed. What were the objectives of the field campaign? Well, to track atmospheric and terrestrial pathways of AR-generated precipitation, as well as runoff in the upper Nechako watershed, to understand precipitation formation, distribution, and extremes on the western and eastern slopes of the Tatsa Ranges. So the Tatsa Ranges are part of the Coast Mountains. And then as well, very importantly, to train highly qualified personnel on the operation of state-of-the-art meteorological and hydrological equipment, weather forecasting, storm monitoring, data analysis and interpretation, remote field work skills, as well as outreach. here's a slide that depicts essentially the study area as well as the experimental design. And I'm not sure if you can see my mouse, but the inset map shows the Nechako watershed. That's the red outline. That spans about 47,000 square kilometers in northern British Columbia. The white dots indicate 6 primary field sites that we had. So Skins Lake Spillway is on the interior plateau. The black rectangle here shows the primary field sites that we have on the left. I'll come back to that in just a moment. We also wanted data near the coastline. So at the inland coast, we have Camano. Again, this is where the Rio Tinto hydro power facility is situated, and as well a little bit further to the north in Terrace. So that provides us essentially a longitudinal profile going from near sea level at Camano towards the interior plateau, of course, going through the coast mountains. And then on the left-hand side, you see the map. Our primary base of activity was Huckleberry Mine. So there's not a lot of locales in this area. So Huckleberry Mine provided accommodation, AC power, we had access to the internet. So it was a great home base to do essentially our meteorological monitoring. And there we had a number of precipitation gauges, we had a microrain radar, we also had a laser disdrometer. So a variety of instruments, as you see at the bottom right here on the picture, collecting meteorological data. In 2 nearby creeks, we're also collecting some hydrological data, so stream temperature, water level data, as well as discharge measurements that we were collecting after the storms had come through. We had a network of tipping bucket rain gauges to capture elevational impacts on precipitation. And I want to mention at Huckleberry Mine, we also were doing storm observations every 15 minutes during the heaviest precipitation events, as we were doing as well at Nadina Lake Lodge, where we had another group situated there, sort of in the rain shadow of the coast mountains. And finally, at Huckleberry Mine, we were also launching radiosondes during or prior to some of the major events. So quite a suite of instruments that we had deployed across the upper Nechako watershed and as well at Camano and Terrace. Well, we had obviously some very nice sites to work in the upper Nechako and at Camano. So at the top left, you see a picture here. There's an Environment Climate Change Canada weather station there. Again, this is close to sea level towards the coast. Very wet area, on average, something like 2,500 millimeters of precipitation. And you see a microrain radar as well as a disdrometer that was installed there for the duration of the field campaign. Mount Sweeney, so this is close to Huckleberry Mine. There's a national old mining road that goes up into the Alpine. We were able to install a weather station sort of at 1,400 meters in elevation, including an all-weather precipitation gauge. Some of us were staying at Nadina Lake Lodge, and we had a standard precipitation gauge that we collect data every day. And want to actually thank some volunteers like Chislata Kara Nation towards the Skin Lake Spillway that were also collecting some precipitation data for us. We had 2 volunteers there adding to our database of precipitation data. At the Skins Lake Spillway, this is where water is released from the Nechako Reservoir towards the Chislata River and ultimately the Nechako. There's also an Environment Climate Change Canada weather station. And so we set up a microrain radar as well as a disdrometer at this site. Nadina River Spawning Channel, this is a DFO site. And we had a tipping bucket rain gauge as well as a full meteorological station on site. This was the sockeye salmon spawning season from mid-September to early October. So we were challenged at times by grizzly bears, and we had to bring the dog, as you can see, to spot out the bears for us. And then at the bottom left here is UMBC's Northwest Campus. On the rooftop, we had, again, a disdrometer, microrain radar, as well as a full meteorological station. And I want to mention that we were collecting high temporal frequency data, for the most part, either 1 minute or 5 minute data for most of the instruments. Well, the challenge, of course, is going into a field campaign. You don't know whether you're getting a lot of storms, but as you heard before in the talk, for instance, from Dr. Mo, it was a busy AR season along the BC coast. And on the 21st of September, we had a direct hit, our first landfalling atmospheric river, as you see in this composite image from Meteo Blue. So we have clouds as well as the precipitation rate inferred here with the scale on the left. And you can clearly see this atmospheric river was coming down actually from the northwest towards the southeast, hitting Haida Gwaii at this time, as well as Prince Rupert and the Red Star, which is our TRER study area. So we were quite fortunate to actually have a couple of direct hits by atmospheric rivers over the duration of our 2-month field campaign. Just to give you a sample of some of the data that we were collecting. So here we have microrain radar data. So this is a radar that's pointing vertically. This is Huckleberry Mine over the duration of that atmospheric river on the 21st of September. Vertical resolution is 50 meters. We're collecting data every minute. We had data up to 6.4 kilometers above the ground level. You can see the radar echoes intensifying, particularly between 800 and 900 hours. The maximum are maybe of the order of 40 dBz between 10 and 1100 hours. You can also see the melting layer. So that change in the reflectivity as it intensifies as the snow melts into rain, and that melting layer actually decreasing over the duration of the event, perhaps due to cold air advection aloft. And the bottom plot actually shows the trace, the vertical velocities for the hydrometeors. Aloft, you see that obviously we have low velocities associated with the snowfall, and as the snowfall melts, it accelerates. We see vertical velocities of the order of 6 meters per second near the surface. As well, we're collecting rainfall and some water level data. So the right-hand panel here shows the cumulative rainfall for that atmospheric river on the 21st of September. Again, we were at a range of elevations, and it's interesting to compare essentially the data from these tipping bucket rain gauges. Typically, we did see higher precipitation amounts as we rose in elevation, and over the duration of this storm, we saw about 50 millimeters of precipitation over the period of 2 days. And then on the left-hand side is a trace of the water levels that we're collecting in both Whiting and Ryan Creeks, I believe at 15-minute intervals. And you can clearly see the jump in the water levels on the 21st of September. So an increase of about 40 centimeters very quickly during that atmospheric river landfall. And then, of course, it comes back down afterwards, after the event has subsided. And on top of the water levels, we wanted to collect discharge data. So we had a flow tracker and people going into this very cold water, which was about 2 degrees for the most part in the fall, taking discharge measurements after the storms. And from that and the water levels, we can derive a rating curve and then get a time series of river discharge as well. Some of the outcomes, well, we can see more men than women were participants in our field campaigns. So that's something we have to improve in future field campaigns and have a better gender parity in our team members. You see the distribution of our personnel, and that includes myself that participated in the 59 days that we had in the field, 15 field sites, and we collected a huge amount of data, 75 gigabytes overall for those 2 months of the field campaign. 250 millimeters of rain or precipitation at Huckleberry Mine, 11 storms of note, and that included 2 direct hits in our TRER study area with atmospheric rivers, 1 atmospheric river on the north coast, a little bit to our north, 2 further to our south, and then 6 storms that were not related to ARs. And then we had 11 weather balloon launches, again, giving us at the second scale, some profiles of the atmosphere up into the lower stratosphere. Well, we wanted to query our participants in the field campaign, what they had learned as part of this 2-month field campaign. And so we assembled these quotes essentially, and for many of them, it was perhaps their first field campaign. So they learned how to assemble, operate, download data, decommission state-of-the-art meteorological equipment. Some learned that local topography plays a huge role in precipitation accumulation. Others learned how to use the tipping bucket rain gauge to measure precipitation as well as air temperature, how to be safe in the wilderness, field safety protocols ready for all situations, trusting your partners, particularly important in grizzly bear country, connecting what they learned in class on mountain meteorology to the mountainous environment they were observing firsthand, taking discharge measurements for the first time, enjoying it even though it was cold, and the importance of making sure your colleagues feel good, checking in with them, asking questions when doing remote and isolated field work, and then meeting researchers from different backgrounds and fields of expertise, because some were more focused on a meteorological background, others on a hydrological background. So what's next? Well, we're obviously doing the quality control and analysis of all the data we collected. So that will be deposited in a public data repository in the near future. We're also working as a team on a publication that will be submitted to a journal that will describe the data set. And of course, we have all these data to analyze. So we have a PhD student, Bruno Sobral, Dr. Mo is part of his committee, who's looking at the terrestrial response to atmospheric rivers across the Chaco watershed, and to be looking at some of the data that we collected during TRER. And then as well, we're hoping to improve meteorological monitoring of atmospheric rivers and other extreme events in north central British Columbia. And this is through the MESH Observatory. So Dr. Julie Thériault at UQAM and I were successful in a CFI and BC KDF grant. And we'll be able to set up now permanently microrain radar, laser disdrometer, and other meteorological equipment at both UNBC's campus and terrace, as well as Huckleberry Mine, to get long-term time series on atmospheric conditions during these ARs and possibly other extreme events. So that's next for us in terms of research. And Mindy, that closes my presentation. And I just want to acknowledge that there's a huge amount of people that were involved in this field campaign. I want to thank Kelly Hurley, the project manager who ensured the success of the field campaign, our funding partners, Rio Tinto, Natural Sciences and Engineering Research Council of Canada and UNBC. And we had a number of colleagues at McGill as well that lent us some equipment, and other participants, Selena Mitchell, Jingwang Wu, and Pierrick Lamontagne Abbé, who participated in the field campaign, and many other groups, as you see on this slide. So I'll leave it at that and welcome any questions or feedback.
Oh, Stephen, what a great talk. And just as a senior scientist in Environment Canada, we really look forward to having more good people apply for jobs with us. It is
Yes.
so essential to work with universities and have those people. They make excellent employees, and they know what needs to be done. And also, I'm really looking forward to your MRR and your other data that you have. Realize we have an MRR at Squamish as well, and the
Right.
only one we have. And I've looked at it for years, and we really could do with other instruments. So really looking forward to you. And we have 2 questions here.
Yep.
If it's okay with you. And we also, have about 13 minutes on the session we could go.
Okay.
Yeah, I can grab Serena. Finally, I'll see your question first. Do you have any plans to continue this field research or do anything similar this fall?
Yeah, unfortunately, we don't have a specific field campaign plan for this fall. With obviously the equipment that we'll be able to purchase for the CFI BC KDF, we might be able to install some of the equipment by this fall, but we don't think the microrain radar or the laser disdrometers will be installed this fall, probably by sometime in 2023. But we're certainly looking forward to other opportunities to undertake another field campaign like this. It does take quite a bit of resources. It took over a year of planning and preparation, and obviously some financial resources to undertake such a big field campaign, but we'd love to do it again. And I know Dr. Julie Thériault and perhaps others would be excited about a phase 2 to TRER. So certainly something to consider, but at the very least, we know we'll have some equipment for which we can actually monitor at least at 2 sites, atmospheric rivers and other extreme events over a longer period of time rather than just the 2 months that we had for TRER.
Yeah, that is really good news. We have another question from Rupin. He really liked your experiment, like we all did. He said, much of the watershed, your experiment focuses on is located in the rain shadow areas of ARs from the Pacific. Can your collected data show how significant the spillover of precipitation is, and what is a typical distance of the spillover can go beyond the ridge of the coast mountains?
Yeah, that's a very good question, Ruping. And that was part of the motivation for us to have a site right at sea level at Camano, at Huckleberry Mine, which is somewhat in the lee of the, the highest peaks of the Tatsa Ranges, and then onto the interior plateau at Skins Lake Spillway. So using, for instance, the microrain radar data that we have, we'll be able to track that moisture as it moves inland and how much of it is residual and how much precipitation we also get into the interior plateau, which is, of course, of great importance for our industry partner, Rio Tinto. They want to know how much precipitation falls not only in the mountains, but also across the upper Nechako watershed, which spans 14,000 kilometers, most of which actually lies in the rain shadow of the coast mountains. So just to give you an indication of the impact of the coast mountains on the precipitation in the interior plateau, Skins Lake Spillway, the Environment Climate Change Canada Weather Station, receives about 400 to 500 millimeters of precipitation annually, whereas at Tatsa Lake, we get 2,000 minimum. So big rain shadow effect. So yes, very important to explore that rain shadow effect and how moisture is transported inland from those atmospheric rivers and other storms as well.
Well, that's great. I have a question as well. A lot of times in the BC interior, forecasters keep their eye out for storms that may come in a bit westerly to northwesterly direction. So there are some angles of the atmospheric rivers that are particularly impactful and get into the interior. I know the same thing goes like for Kitimat area. I wonder if you could comment about what maybe you would be doing or could do on the direction of the AR.
Yeah, that's a very good question, Mindy, and something we did not explore so far. But the orientation of the atmospheric river is particularly important. Like you saw the mid-September event that we had, the 21st, was from the southwest towards the southeast. The axis was oriented towards, for instance, the channel going into Kitimat and Terrace. So we'll be able to track that transport of moisture inland again, because we do have a site that was in Terrace, about 60, 70 kilometers inland. So it is something that through the case studies that we did experience in 2021, we'll be able to look at the orientation of the atmospheric rivers. And again, the orientation is so important when you have a valley that's oriented in a given direction. If it's aligned with that valley, more than likely have greater transport of that moisture inland. So definitely something to explore.
That's great. Let's see, I don't see any other questions, but I always have another question is, if you could do, like, what do you think is, have all the money in the world to do what you want, which doesn't really happen, but sometimes if we work together, we can. What would be a project or a locality that you think the university, for example, could really work with government and other agencies on?
Well, it would be great to get a research aircraft into some of these storms and probe them, as they head towards the coast. Another issue that we have, on the north central coast of British Columbia is we have no weather radar. It'd be great to have, some sort of radar eventually installed in that region to get more data on precipitation regionally, rather than just vertically pointing microrain radars. There's a lot you can do. There's a lot of research to be done. Certainly, be interested in participating in any other major field campaign if Environment Climate Change Canada wants to do so, and maybe other government partners.
Well, we're very interested, and obviously we've got a lot of concerns about global warming and changes coming very fast, and it's really good to have experts like you working on trying to anticipate the change, because it has a lot of people very upset how fast we're warming our climate and the impacts. So, I mean, we do have a few more minutes. Could you comment about what you think and what your concerns about climate change and what we might be able to do better with research in that area?
Well, again, for Rio Tinto, it's all about water replenishment, and they're particularly concerned, obviously, in terms of summer droughts in the future and how that might affect water resources in the Nishaka watershed. But in the fall, we might get more and more intense atmospheric rivers making landfall. So perhaps a change in the seasonality of the precipitation, perhaps coming in more intense and short duration events. So that's harder to manage when you have a large reservoir. Something to think about. I know we had some presentation last year looking at this as well, and that the future frequency of atmospheric rivers is likely to increase substantially across north central British Columbia. So definitely we need to keep tracking these events. And I think this is just the start. We need to have more field campaigns like this to better understand these events, to better model them as well and predict them. So a lot of research ahead of us.
Yeah, well, thanks. I appreciate what you're doing. I don't see any more questions. There could be a question on any of the other talks, but otherwise we'll end our session 5 minutes early. Are there any other questions or any last words? Well, I don't see any. I wanted to thank all of our speakers. You're really terrific, and it helps all of us to come together on this. And I'm really impressed at the work, and thanks very much.
Thank you, Mindy. Thanks for hosting this session.
Okay. So we'll end the session now. You can stop recording.